哎，这个得关地盘的把人家反光。
OK，
当真
OK，before we discuss assignment, yesterday we left with one exercise. Okay, so can everyone try this one? Based on what we have learned yesterday, see if you can try figure out what is it. Okay, so even like this kind of question, right? Even before you start, right? You should check that it is possible to write first before you try to write one down. Yesterday will give a equivalent condition how where can a number written as a sum of three squares, right? If you still remember, which is this special form here. Okay, if if it is not in this 4 to the power times n form, okay, then it can be written as a sum of three squares. Okay, so you should try and see whether this is not the form that we like. If not that, this prime factorization of 1897. Okay. So it is not in the form of 4 to the k times multiple of 8 plus 7. So it can be written as the sum of three squares. Okay. So then the next question is how to write this as a sum of three squares. Well, so yesterday you see a technique, right? We can first pull out some even power, because if we can write the rest as a sum of squares, then this even power can be just distributed to every term later. Okay. So which I find my connected stuff. They are trying to connect again. Yeah. Okay. So so I try to pull the even power out first, because later if I can write the rest as a sum of squares, then this even power can distribute into the terms. Okay. So then we left with a question that can we write the smaller number as a sum of squares? Okay. But then if you look at this prime factorization, right, it is not in this form either. Okay, it's not in the power of 4 times 8m plus 7. Okay, there's only a 2 here. Okay, so similarly, we could write this smaller number here, which is 210. Return as a sum of choose. Again, without loss of generality. So we're going to play the same trick. We're going to play the same trick with this three numbers here. So let's write it as x squared plus y squared plus z squared. Okay, so we first restrict ourselves to less number for checking. So then your x should be less than or equals to square root 70. So what's roughly about square root of 70? Should be less than 9, 8, around 8. So it should be less than 9. Okay. So then you should try 8, maybe. Okay. So let's say we try 8. So after we try 8, so we ask the question whether 146 can be written as the sum of 2 square. Well, then what do you do here? Well, similarly, you play the same trick again. Y should be less than or equal to 8. Say this because square root 66 should be less than square root 73. So square root 73 or square root 73. What's square root 73? Add on something. Is it add on something? Okay. So this guy is less than 9. So then, so you have 8 choices to try again. Okay, maybe try 5. So it turns out that 5 will work, and we are good. Okay. Basically, what we did now is just try and error. Or try and error doesn't mean that you try once it works. It means that you try and error. You will meet error. So far, any question? Is it clear? Yeah, question from here? Either? Yes. Okay. Yeah. Okay, so this, you see, we start with this estimating trick, right? This kind of trick. Then you started with this trick when we try to find prime divisor, right? Okay, at the end, we still end up with this kind of trick. Okay, so this kind of estimation trick is quite important for number theory. Because back in the day, they don't have calculator, right? So they just play around with these inequality. Yes.
这时候只看出来怎么样？
什么？不是看出来哈？by inspection 只看出来 inspection If you just, if you just try an error and then hit it once by chance, you could write something like, okay, so maybe I give you an example. So maybe it says that, write 5 as a sum of 2 squared, for example. Okay, so maybe one possible solution we mathematician can write is like by inspection, I equals to 2 squared plus 1 squared. 看出来，直接看出来。Yeah, there's something like that. This is the special term for it. I can see it. Because it's also easy to verify this system. Okay. Yeah, just that we need to give you some systematic way to do, because this will be working in general. Because sometimes inspection is very hard. Usually you have to try and error. Inspection usually come easy when you do a lot, when you are experienced. So how are you getting experience? Try and error. Because you try a lot. Otherwise you don't have experience. Your experience will fail. Right? So you try and error a lot, then you get experience. Okay. Any more questions? Also no question. No. Good. Can follow. Yeah, so finishing the slide, we finish all the slide in your notes already. Okay, any question or specific question you want to ask? If you want to ask about an exam, tomorrow I can give some tips. Or you can ask now, but I won't answer yet. Let me collect your question and I can know better how I'm gonna answer you. Okay. Yeah, so far we have gone through 7 chapters, right? So first chapter is what? What is it? Huh? What? Yeah, what is it? Introduction? Our introduction is about what? Prime numbers? Is it the introduction? The GCD? Prime numbers? Sorry? LCM? Okay, good. For now, 2 numbers is just GCD times LCM. Second chapter, congruence. Okay, congruence. Chinese remainder theorem. Fermat. Slater theorem. Euler's theorem. Phi function. Okay. And then next chapter, multiplicative function. So we deal with a lot of multiplicative function, like calculating integers that are relatively primes, and then what sort of special function, numbers of divisor, and what sort of special function is it? Sum of divisor. Oh, sum of, yeah, okay. So you calculate how many of them, or you can try to sum them together. Okay. Any others? So if you take the big sum, of multiplicative function indexed by the divisor is also multiplicative. And what's after multiplicative function? Sorry? Primitive roots, good. Okay. So primitive root, we deal with the order, right? Order of the elements. Okay, when the order of the elements equals to phi n, then it is a primitive root. What's the advantage of being a primitive root? So if you take all the powers, it will consist of all the relatively prime numbers to n. And that's the most important one. Okay. And then after primitive root, cryptology. Cryptology, is it? Yeah. Okay, so cryptology, you do with a cipher, Caesar cipher, shift cipher, RSA, the block, right? Or in block. What else in cryptology? That is it. Just until RSA. Anything after RSA? Sorry? Oh, that's the next chapter already. Chapter 6. Oh, okay, sure. So chapter 6, quadratic residue. Okay, so meaning you ask a question on x squared, what's the solution of x squared equals to something? Or if you square a number, what do you get? And what's the residue of it? What's the significance of this one? There are Legendre symbol, Jacobi symbol, okay, to tell you when there's a number of solution to, oh no, not so, yeah. When does x squared equals a, for example, has a solution? If a has a solution, meaning a slash p is 1. If there's no solution, a slash p is -1. Okay. And then finally, we reach this some non-linear divergent equation. Okay. In particular, we learn sum of 2 square, sum of 4 square, and sum of 3 square. Okay, so the most versatile one is sum of 4 squares. Okay, because every positive integer can be written as the sum of 4 square, but not sum of 2 square or sum of 3 square. In that case, we are not interested in sum of 5 square already, because we already can write everyone as the sum of 4 square. Yeah. So meaning 4 digit of number is enough to represent all the integer if you allow squares. So I think throughout this course, right, there's 2 powerful things you see, right? So every integer can have a prime factorization. And so meaning you can split it as a product of primes. Okay, you're right. So first is you can split it as of primes. Second is you can split it as a sum of 4 square. This is true for any integer, but here is positive only because it's sum of a square. So every term here is positive. But this is enough to do for negative, right? Because you can just multiply negative. Does that make sense? No? Okay. Sorry. Try again. So let's say if I have a negative integer, n, then minus m should be positive. So I can write minus m as a sum of 4 square. Then, yeah, then m, I need m, right? So I can multiply minus on both sides. I can push the minus to the other side. I'm not writing it as a sum of sum of 4 square, but with a negative sign. This is what I'm going to say. You could never you could never write a negative integer just with sum of squares because square should be positive. Yeah, but with a minus sign. But then it's enough to represent the number. Okay. Any question on these points here? So this is what I teach so far. Maybe you can say like, what's the main thing you most impressive or most I'll say catchy or you remember? Huh? Maybe we can start from there, one by one. You can say what's the interesting thing you see here that you can recall? At least one by one. Let's say from Seng什么题？对，这是什么最有印象呢？你学了这么久，这5个星期。对，或者就你最冲击你的，之前可能没有看过，或者
就是昨天认识的这种，
不是 sum of four squares。
对，
OK，
因为不是说了所有的奇质数都可以由这4个组成嘛，然后2也可以由这4个组成，那就是说所有的质数都能由这个组成嘛，然后又学会了，一个如果2个相乘，2个都可以由4个组成，相乘之后它的那个也由4个组成，那也就是说。因为质数所有数都是由质数相乘得来的嘛，然后那就能证明所有的数都可以由这4个组成嘛，觉得比较神奇。
I see. Okay, so you were saying that because if you could write, so even before this result for integer, right, we have a theorem saying that every prime can be written as a sum of 4 square, and then we combine with prime factorization, we could write every integer as a sum of 4 square. This is what he said. 能够用他说英语，所以我不用transfer。你说什么？说什么？What? OK， 这个课上的东西，课上的东西。
相互那些定理相互来回串的。
OK，
来回定来回套的。OK， 挺有意思的，对，
挺难。OK， 好。OK， so you were saying that the logic that we see in chapter 2 and chapter 3, how we use definitions to prove theorems and then use them to prove theorem, use different statements that can imply different statements. It's very interesting. Okay. So assignment. Assignment 2, yeah. Yeah, so the last question, usually people use Fermat-Leysen theorem, but then they are restricted to GCD is equals to 1, but actually that theorem has a corollary that you don't need GCD equals 1, but you have some weaker result, but then weaker result is already enough for you to solve it. Yeah, so you don't need to go to a more restrictive case. Next. That's okay. Maybe you can think about why you come to this course and then does it meet your expectation or you get what you want to learn?
There's a lot of things that you could take out to solve it. That's how the word say it's like it's actually learn to sing by yourself.
Okay. Okay, good. So you're using AI to learn now? Good to understand. Do you find it useful? Do you find it useful? Right. Is it helpful?
Yeah.
Good. Okay. Next one.
就是觉得这一个简单的书的细节特别的操作就非常的有意思，而且也比较设计。
然后呢？
就是像一个数字反面的两个字平方，数字的平方和形式还是两个人，非常的细致，感觉到这个数学之间的魅力非常的有意思。
Okay, so he is like interested in the structure of numbers. Okay, like product sum of two square is still sum of two square. Okay, so this operation I respect these kind of structures. Okay, thanks. And so probability of congruence build the foundation of the later proof. Okay, good. Right, Tiffany. Okay. I see. Okay. Yeah, first year, right? Yeah, first year. Okay. Ah, okay. But your foundation is business or IT. Okay. I think they don't learn this as well. Yeah. I think none of them learn this unless they take discrete methods. But then this would be the how to say intensity for the university level course. Yeah, intensity will be like this. Although this one will be more intense because we learn 3 times a week. But then the content is about this much every week you will see. Next. Oh, interesting. What degree are you? Huh? What's the degree?
CST. Oh, CST. Hello.
Wait. Hello. Okay. CST. Which year are you in? First year. Okay. You still have time. You can change your degree to MSc. If you found this interesting, you should change them. Thanks. Okay. The question in red. You mean like assignment question?
What should they say?
the most impressive thing we learned.
Yeah.
Pretty basic. Fact that every number can be a unique product of prime.
Okay, you like that? Okay, cool. Okay, next. Of cryptology, okay, how to make some secret so that people can decipher or cipher. Cryptology as well. Okay, you also from CST? You also data science. See the similarity. They like cryptology. Okay, next. Are you? Yeah. Can you tell us like what you learn? What you learned in this course? Complex? Complex answer? Sorry, I get you. Maybe can you speak a bit?
Is learn how in questions and then compare
The city of the answer? That what you mean? Okay. The gap between simplicity of the question and the complexity of the answer. Wow, very philosophical answer. So it means that your answer, your question is easy to read, but your solution, why is it so hard? Okay, yeah, yeah. I wouldn't say it's hard. I would say it is rigorous. Yes, I'll say it is rigorous. Okay, we try. Why actually? This is a very important point in mathematics. That is why are we trying to be rigorous? Why we need to be rigorous? Okay, it's because we want to convince people. Okay, if you are not rigorous enough, people won't be convinced. Okay, people could ask you why like that, why it has to be like that. Okay? So we need to be as rigorous as possible so that we can convince people. Because many people say that mathematics is for like crazy people or clever people. This is not true at all. Okay, this is not true at all because we are the kind of the most stupid person in this world. Why? Because we need to define everything. Everything we need to define before we start working. You understand? Okay. Yeah. So we need to start with definition. Okay, so this makes us different from others occupation, like physics, whatsoever. Okay, because they work with experience. They work with they work with their own I would say intuition. We also work with intuition, but then we'll try to define our intuition first. Okay. We try to list down our intuition, but then sometimes I'm not sure you have a experience or not. Like people explaining to you, it's trying very hard to explain to you, but you still cannot get it. You just still cannot get it. Actually, this is not your fault, you know. This is not your fault. Because there's one important thing in the mind of that person that he maybe don't even realize, and he didn't tell you. You can try and test it. This theory always works. Okay, or that person miss out something that you miss out, okay? Or you confused with what he said. So being rigorous will try and remove all this confusion. Okay? So that's why mathematics is hard in that sense. Okay, we try to remove all confusion. Okay, yeah. So we try to list down as many conditions as possible. Right. So you can see that in this throughout this course, right, there are statements like if what then happen, if then, if what then happen. Yeah, only if and only if, then it will be an equivalence statement. Okay. There's no left out information there. You remember yesterday I showed you something like this. understand. Yeah, this one. Okay. So if you go this direction, right, you can't go backward. You can't go backward. Wait, let me see. What am I doing there? Oh yeah, sure. Okay, so this direction. So if you go this direction, right? Okay, you can't go backward. If you want to go backward, you need to add one more condition. Okay, so meaning backward direction is missing some information. This is what I said. If you add enough information, then they are actually the same thing. What I said. Okay, maybe we can go to the next one. Proving. Okay. You read prove yourself. Okay, so you also from DSC. Huh? COS, I see. Good. Okay, very good. Next. Here, language, the two. Okay, maybe you can try and Euler theorem. Okay, you like Euler theorem. Okay, good. Next. Say what? And this one. You like to do question? Maybe, yeah. Oh, not so like. Okay. Okay, next one.
I used to do some math yes, so I learned about stuff like grammatical how to use exponents, stuff that's not covered here, like visual principle, coloring, problems, stuff like
Good. Very good.
but I was only taught like the formulas and how to use them to solve
Good.
questions. I never learned the theory behind it, so it's very interesting.
Okay. What degree are you in? Oh, you're not interested in looking. I don't know. I see. That's sad. Okay. Good. Actually, pre-adjustment principle is being used in the proof of some of the terms. Yeah, if you notice that feature. Coloring. Did you mention coloring program? Yeah, color program is actually a very. Is it for color you mean or? Sure. Definitely. Yeah. In particular, there's a problem called for color here. Yeah, so there's a partition, I guess, can be filled with emeralds for color adjacent the conjunction, but they prove it in different things. Very important problem. Okay.
Continuous fraction within in the rational number and irrational numbers it's real all integer.
Okay. Yeah, I also like that one actually. What's your degree? So which area? I see your assignment is also quite good, quite consistent actually. I like your assignment. Okay. Did you mention prime decomposition? Did you mention prime decomposition? What are you mentioning? Decomposition. I said it. Okay, good. Okay. Next. Legendary symbol. Okay. Okay. Okay, good. Okay. Well, sure. Okay. I said recording. Okay, good. Introduction. Okay. Per month here. Liter or last? Last. Okay, good. Yeah. I also like that kind of instead of listing down some. That's
This is the primitive roots and the connection is the next chapter. As we can use in index to drop
uh,
to like multiples into.
okay, sure. Yeah. So that one is very important. So when you go into abstract algebra, that will be very important. Let's see. Are there procedures? Okay.
Cryptography.
Cryptography. Okay. Next. Joseph cryptography. Okay. Wow, seems like most of you like cryptography. How about sardine? Sardine. Huh? Are there procedures? Okay. Why? Huh? Easy to solve. Ah, okay. Easy to solve. Okay. This could be the reason. Yeah, anyone will. Very interesting. Okay. You are from, you have discrete math? I see. Okay. Good. Where are you from? Tunisia? You speak like one of the lecturer, but he's from Iran. He's from Iran. Is it close? Not close. Maybe same ancestor or what? Okay, not from yeah. Quite far, Iran. But I mean, like you guys have the same outlook and then same way of speaking. I guess. Huh? Yeah, sure. Maybe, yeah, sure. Maybe I guess like they moved long time ago or what. I don't know. But it's really similar the way of speaking, and then maybe the outlook or something. Also, cryptology. Okay. Creative group. Okay, good. Hey, where are you from actually? Degree. E. Okay. Good. Okay. So, right. Should we take a break? And then we'll come back with assignments. Okay. Let's break until 10:06.
Yes. Should we memorize all the theorems? You need to be familiar with those we are using. Yes. For the other? For other? I mean, are you going to like which parts should we focus on? I could tomorrow I could like try and pin down like which section you need to pay more.
But I really like because
Oh yeah, that's fine because I know that sometimes it's very hard to converse. When you think about I try to do bilingual because I can do bilingual. So, yeah.
you're also trying to record sessions.
Yes,
So students to talk about.
definitely. That's okay.
对恶魔包个truth。
还没吃啊？确实，
没有那个，他没有到。
我今天也是吃的。不要什么？
是第二天，教完了，教完了。不多我也还没到我这个班。你转告一下我，留下我。啊，不是，转告一下我。就上一圈下公司，有回信。Good. 真是。然后还是。他会。再打一个有问题。明天的话，明天打。真的，我这个一点还不错。在吵。是打赢没带。哦，如果再过2年，应该。哦。然后我想只会玩这个小分安全。你看，大概这个，让我想想，这个把一个弯是完结。哦，OK OK，啊，对，或者重新写过，谢谢。可以，没有错，谢谢。这个应该叫。这个像我在看，感觉我的脱离啊，怎么嘞？不知道，我感觉我有点干，又不是用跑式，我放底下把它拔下，我下我聊一个东西先到啊，有好，然后再看，OK， 要。我们每个人在跑，啊，需要。对，这个有没有？这样子干嘛用？那就礼拜几？这是好的。啊，对，今天下午2点。整天都有啊？对，全部人都跟我。也是因为要去我的教区来发展办法的，然后就这里有3个老师会。我们整天都有，那开始。哎，你看他那个楼梯，A4 楼梯贴，电梯都有贴的，太棒了。可以来，好，我可以来。你来个比分吧。同那个 special guest 还有 bomb tank。有没有玩？当时你昨天晚上那个是用牌啊？对，也是 AIT 的，也是 AIT 的，没有 B 的，没有大 IT，单年的，单年。我教了那1年 AIT，过没有教到 AIT。我们新北还认识，我们说没认识，真的可能会认识啊，概率挺大。我发给他们，跟上一个，能认识哎，20到20，还开始更大，还真可能。
延迟几个月
没有怀生素还是校园的情况嘛？
你念出
有就有一个难做。
马来西亚人，马来西亚人，
哦，马来西亚人不认识西亚人，不认识的，有的。
中国人的话就打过一次。你念错，你念点
我知道4年滑雪会
啊，金浩知道。
哦，
好了，子涛也选过，子涛也是玩者。
哎，我不知道，这么玩的，
我也不知道。
对啊，
他是毛单位啊，
他玩的
什么王者多少钱？
应该蛮多的，
蛮
多。
那个酒为什么打王者过来的？不知道。
进去了。
那什么时候卷啊？
哦，子涛，会有人治他们？对吗？同一个 supervisor。
哎，
哦，
这是你们系的
一个系怎么会认识？你不同届。
大区，
有语大区，
大区和整个系的区，每届毕业的都在。
对啊，对啊，对啊。
老师只是同时打王者，要扩展自己的人脉吗？
没有，以前没有打，就这两个月3个月，没干时间。
我打了半年才上5个人。
没有有人带，
好，
有人带，那我
放给他。你都没有这样多历练吗？
没有他做的，蛮
不是卖掉了，那边水了。到现在你不要这样努力。
没有他的办法。
20年那边，我花了钱买了。
不是
以后先给他又出一个2个嘛，等再回点。
Okay, let's resume again. So very good observation from one of your friend here. Seems we already assumed x less than or equal to y less than or equal to z, right? If you look at the sequence that we found the solution, right? Actually, we found 8, we found 5, and then we found 11. Okay, so it's not in the order that's written here. Although this is not a big deal because we still solve the problem, but then there's a logical problem here. Okay, because we already assume an order here. But this is easy to solve actually. Okay. One way to solve it is I could start with 8, start with 5, and then 8, and then end with 11. Because you can treat this as a working, just as a working. And then when you present to people, there's a different thing. Okay, so in mathematics, there's 2 things you need to remember. One is working, one is presentation. Right, so that's why sometimes, right, I will deduct mark on your presentation if you don't answer directly to the question or it's not clear. Okay, so presentation is important. So one way to solve it is this. I can pretend I found 5 first. Okay, and then I found 8, and I found 11. Then this is in the right position. Okay, this is one way to do it. Okay. Otherwise, you can rewrite the proof, meaning meaning you found that one of it has to be 5, and then you start a new argument saying that, oh, can we found 1, 4, 6 as a sum of 2 squared or not, and then restart every part. You understand what I say? Yeah, instead of going through the same assumption, you can restart the proof in every step. Does that make sense? Okay. Although this is not ideal for solving the problem, but then there's some logical problem when you present the solution. Okay. Yeah, very good observation. Okay. Any more question? No. No, then I will just go to the assignments. Right. So let's look at the assignments here. So our first question, there's a lot of part. I mean, every question has a lot of parts, small part. First, find the order of module 42 with justification. So basically, you find what is phi of 42, and then the order should divide this phi. So there are just 1, 2, 3, 4, 5 possibilities other than 1. Then you just prove that when did you first get 1 when you take the power of these choices. So it is 6. Everything before 6 is not 1 powers. Okay? Yeah, very straightforward. Next one, determine whether each following positive integer has a primitive root. Okay, explain the answer. So we have a theorem, right? Okay, so we have a primitive root if only if it's in 4 forms, right? 1 is 2, 1 is 4, and then power of primes or 2 times power of primes. So just write down the prime factorization. Does it look like that? If it's not, then no prime primitive root. Okay, if yes, then there is one. So it's no, yes, yes, no. Okay, first of all, is 2 is not a odd prime, right? Okay, so prime power refers to odd prime. You have power of 2 that has primitive root only up to 2. So 2 and 4. 4 is 2 to the power 2. And then here, the fourth one is not twice the power of prime, odd prime, okay, because you have an extra attribute. Okay, next, for each integer in part B that has a primitive root, find a primitive root of n. So there are 2 of them, right? 169 and 338. So from here, you should realize that there's a relation between 169 and 338, right? So 338 is a twice of 169. And we have a theorem saying that once you found primitive root for power of odd prime, then you will know twice the power of it. Okay, by adding what? Adding 169. Yeah, adding a odd power to it. Okay, so that means you just need to find the primitive root of 169. But some of you, you found again a primitive root for 338. It's okay. You just need to prove it. So you have more work. Usually you start with 2, right? Because we say that 2 is the primitive root for most of the cases. So you start checking 2 first, whether 2 is a primitive root or not. Okay. Any question for first one? Any question? I think for this question, I don't really take marks off because most of you know what to do and doing the right thing. Okay, next, even phi is a primitive root mod 23, find phi k mod 23. Then for each a, table the k. Okay, for this question, I have some comment here. Some of you swap k and a. Okay. There's some logical problems here because you think that a is controlled by k. Okay, but what we wanted to, can I say like that? Let me think. So, okay, what we want here is I give you an a, you give me a k. Okay, it's not that I give you a k, you give me an a. So there's a order problem here. If you say that you give a k, I find you an a, it's just normal calculation. What we wanted is I give you a, solve the power problem. But when you do calculation, it's the other way around. I ask you to figure out what is all the power first. So there's a logical thinking difference here. But I still give you marks. I just wanted to tell you there's some difference. Okay. Use the table in part A to determine all positive integers that satisfy the congruence 12 to the x, congruence to 30 more 33. Okay, so first of all, you realize that 23 has a primitive root, part A. Then you turn everything into base 5. Okay. And then once you do this, there's a theorem says that you can just compare the power, but then it is mod 5 of 23. And then you become a linear congruence. Then you change something non-linear to linear. Okay. Then you go back to chapter 2. This part here, please read the question carefully. It's saying that all positive integers. Some of you just finished here. Do you know that this includes negative integers or not? Because this is a multiple of plus a multiple of 11. So there's negative. So you need to tell me that to restrict to positive. Yeah, this is how you could write it. Like 4 plus 11k where k is not negative. So meaning starting from 0. And use the part. I should suggest we throw C. Actually, C and B is very similar. We should throw C. So we don't need to repeat redundant like knowledge here. So solve 16 times 3 to the 9 congruence to 11 mod 23. So again, you turn everything to base 5 and then you solve the power linearly. I should have suggested throw this question. Next time I will throw it. Because it's very similar thing. Okay, next. Question 2, any question or not? I think for calculation, most of you know what to do, but just that answering question to the point is very important to remind you again. Make sure you know what the question is asking, not just know what to do. Okay, question 3. Find all the quadratic residues of 29, arrange them in the increasing order. I think everyone did well. B, yeah, compute each of the following Legendre symbol. Right. I think everyone is doing okay, but then some of you skip step. Okay, you don't tell the reason. You don't tell this number is like 1 mod 4 or 3 mod 4 minus 1 mod 8, 1 mod 8. And then you just try to compute. So you lose mark. Okay, you lose mark. So please write down the reason. I think I did it in my notes, so please follow that. Sometimes if you just say law of quadratic reciprocity is not even enough, you know. Why? Because there's 2 conditions in law of quadratic reciprocity, right? Okay, if you don't specify the reason, I can tell you most probably you can go wrong. Okay, you will use the wrong condition. Because it will give you 1 or minus 1 depending on your primes, right? So you need to be extra careful. Even for the previous solution, there's a mistake. Yeah, there's a mistake. I already corrected in the latest one. You can try and have a look. For this, the technique involved basically is you can compute the Legendre symbol by modding up into a simpler number, or you use law of quadratic reciprocity to swap the numerator and denominator so that you can make number even smaller, or you can write as a product, right? You can compute as a product. Okay. So in particular, you like the number 2 and minus 1. Okay, 2 and minus 1. So that you can compute the Legendre symbol. For 3, you can't really do anything unless you straight away compute. Okay, otherwise you use you could use quadratic reciprocity if both of them are prime. Okay, so in this case you can do it. Okay, any question for question 3? Maybe get a little more complex in question 3. Any question or question?
No, okay. Good. Okay, for the last one. Okay, this one, the last one. So let n be 2 to the 5 and times 3 to the 3, and let a be a positive integer that's relatively prime to n. What's the maximum possible value for the order of a mod n? Okay, just define your answer. So first of all, you need to ask yourself what are these terms mean. Okay. So order of a mod n means what? You have to solve an equation a to the m congruent to 1 mod n. You have to solve it. Okay, you want to ask what's the largest possible. Okay, but then you realize that so maybe I should write down first. So you want to find m congruent to 1 mod n. Okay. But then you realize that you can instead of solve this, you can make it into 2 congruence, right? Okay, meaning you can split the prime factors of n into 2 relatively prime parts. Okay, using Chinese remainder theorem. Okay, yeah. So you want to simultaneously solve these two. Does it make sense? Chinese remainder theorem. You can split up. So for each of them, so what your strategy is for each of them, you want to find the maximum one and then you combine them. Okay. So for each of these, what did you notice? So the maximum power, okay, how to reach the maximum power? One way to reach maximum power is through primitive root, right? Because primitive root says that the order of the primitive root should be equals to n. Correct? Is it equal to primitive root? What's the definition of primitive root? Phi n. Phi n or n? Oh, phi n, good. Phi n, yes, phi n. Okay. Okay. Good. Okay. So in this case here, you notice that 3 to the 3 has phi n. I mean, has primitive root. Okay. So the largest power you can keep for the phi n here is 5, 3 to the 3. But 2 to the 3 doesn't have primitive root, right? Yeah. But then we have the theorem in the class. We mentioned that although we don't have primitive root for power of 2, right? But we do have element that take power of 5 to the 2 to the k divided by 2. So it reached the second higher. Can I say second higher? I think I can say second higher, right? Second higher to 5 to the 2k. So it's the next level. So meaning this number here, instead of 2 to the 5 minus 2 to the 4, we take 2 to the 5 minus 2 to the 4 divided by 2, which is 2 to the 3. Does it make sense? Or should I show you? Maybe I could show you up here. This one. Okay. This, okay. Yeah, this one. Okay, this one. Okay, order of 5 to the 2k equals to 2 to the k minus 2. Okay, so I remark here. Even though there are no primitive root mod 2k, but there exists an element of largest possible order, which is 5 of 2k over 2. Okay, maybe I can calculate here. 2k minus 2 to the k minus 1 over 2 is equals to 2 to the k minus 1 over 2. So in our case, it's 2 to the 3, which is 8. Okay, so if you want to solve both of these, then you will take the LCM. You want to solve both of them together, then you will take the LCM. So the LCM is 7. But most of you stop here. Okay, most of you stop here. Okay, because maybe I'm not sure it's my problem or not. But in mathematics, right, when we say possible value, right, we want you to find an element to prove that this is possible. Okay, so there's two things we talk about in mathematics. It's about uniqueness and existence. Okay. If it's unique, okay, I don't really care about existence actually. I just wanted to show something is unique. I don't care whether it exists or not. But when talk about existence, you have to find one for me, or make the contradiction. Okay, if that thing doesn't exist, then something will go wrong, even though if you don't find it for me. But most easiest way to do it is find one for me. If there exists, find one for me. Okay, so you have to find one first. Okay. So that part consists of 5 marks. So if you don't do it, then there's no 5 marks for you. Okay, so this question go a bit a long way to do. What he did was he used 32 in school. Okay, he found not primitive root. So this is the thing that has the largest order in 2 to the 5, right? A equal to 5. But then he go and use the primitive root 2 to do it. Right? So they need to combine these two solutions. Then you need to use CRT. So once you use CRT, this number go pretty big. Okay, so it's like 677. Okay, and then I think some of you follow my suggestion, right? Use 5. Okay, because 5 actually is also a primitive root mod 37. Okay, in that case, you just need to verify 5 up to 72. Some of you use 3. I think 3. Okay. That 3 will give you like 500 something. Yeah. It's also good. I think there's at least 4 answers you give me. What's the other one? Let me see. Some of you give 20. No, not 23. Oh, no, not 23. 515 because you use 3 instead of 2, I think. And then you use 7. Is it 7? No, not this one. I think that's it. 500 something, 600 works, and then 5 works. Yeah. I think this is what you gave me. Okay. Yeah. Depend on what congruence you consider here. If you use 5, meaning both of this is 5, I think you use 5 and 3, and then you reach 500 something. Okay, so far, any question? Yeah, so if you have problem on your marking, right, you can ask me, send it to me. For those who have seen me yesterday, I will adjust for you later. Okay, passion, no passion. What should we do next? What should we do next? Should we do assignment 4 or should we do revision chapter 1? Huh? Yeah, no, you can say. It's fine. What do you want to do? Huh? What? 什么？
没有，他讲拜拜。
Bye bye. I wish bye bye too. What should we do? Assignment 4? Okay. Have you tried assignment 4? Yeah, not yet. Okay. Maybe we can try and think about the question together, and then we try to figure out we try to check the solution together. I read it before, but I forget already. So I can also do it at the same time. Maybe you can see how I think about this question. You have solution, right? Okay, let's play a game. So I don't look at solution. Then maybe you can see whether my thinking is on the right track. Okay. Jacobi symbol. Yeah. So definition of Jacobi symbol. So you have to split into products and then see them as a little symbol, right? That's okay. But I think you fell in A. A looks very no. The top one looks very prime, but denominator is not prime, right? So I think you can split up first. So let's see. 143, is it a prime? Feel like a prime. It's 1 less than 144. 144 is a perfect square. Seems very prime. Okay, you can test it. I think it's a prime, but before doing that, if you're gonna split the bottom, right? Huh? 143 is not prime. Okay, never mind. We can do that later. But then we have to split out by denominator, right? To make it into the Georgia symbol. What's the definition of Jacobi symbol? To make sure I don't do the big thing. Okay. Okay, so first thing I will do is I go to the definition. Okay, see? Yeah, I split out the denominator as prime factor and do that. So, okay, how about just split it as a prime factorization? 5, 4, 6. Selection. Yeah. You say 143 is not a prime, so 143 is what time? 30. Huh? What? Yeah, 13 square is 169. Okay, good. Okay, so we can use it later, I guess. So you're gonna split it like this. Okay. I don't think you need to use it yet, right? You can just take mode first. Okay. And then you take mode, and then you should be able to compute, right? 3. The first one is divisible by 3. Oh, sorry. It's the wrong thing. So 3 is so this one is 2, right? Okay, no need to compute, right? Actually, these 2 because it's a square, right? So it's 1 times 1. You need to care about the last one. So it's 3 mod 7. 3 mod 7 can be computed directly, right? Can or not, or you need quadratic reciprocity. And you can use quadratic reciprocity. Otherwise, it's just 1 square, 2 square, 3 square, 4 square, 5 square, 6 square. Do you get 3 or not? Can you use quadratic reciprocity also? So 3 mod 4, right? 7 also 3 mod 4. Sorry? Huh? Oh, sorry. This one should be, this one you have to do something. This is not square. Okay. Like this. Okay. Yeah, so both of these, the number is small, you can like do direct computation. Otherwise, you use quadratic reciprocity. Should we try compute? Okay, let's try compute. So if you use quadratic reciprocity, right, you can directly swap as long as you have a 1 mod 4, right? Okay. If both of them are 3 mod 4, then you have a negative. Let's check. So you have 2 mod 5, sorry, 2 mod 3, and then negative of 7. What's this? 1 mod 3. Last time we proved that 1 mod 3 is always 1, right? So 2 mod 3, 2 over 3. 1 times 1 is 1, 2 times 2 is 4, is 1. Okay, so this is negative 1 times negative 1 is 1. Okay. Maybe if like we can check one answer to give you confidence first. If not confident, then we check what's the mistake. Someone. Okay. Okay. I didn't write argument here, so make sure you write. So here is something 3 more 4, and then 5 is 1 more 4, and then 7 is 3 more 4, like that. Wow, how about this? Crazy number here. Crazy. What's the idea here? What's the first thing you could do here? Screenshot, give to AI. Okay. What's next after that? Anything we know about Jacobi symbol? Anything we know about Jacobi symbol? Huh? Odd numbers? You mean what have to be odd? Huh? Bottom one, not necessarily odd, right? Because this is Jacobi or not the Chandra. Oh, odd. Odd. Okay, thank you. Okay, odd but not prime. Okay, good. Thank you very much. Is it not odd? Oh, all right. Because it's a power of 7 and then plus an even number. It's all right. Okay. But then one way to not calculate this thing is this proposition. If you can find that their GCD is not 1, this whole thing is 0. You don't need to calculate already. This is one way to get around. I'm not sure it's the best strategy, but this is one of the strategies. I think that we don't do much on Jacobi symbol, right? Definitely, you cannot use A, property A, because obviously the top is smaller than the bottom. And then you cannot split. I mean, if you can split the top, it's for good also. But then I think most troublesome one is N prime. Let's see. Or we just directly use law of reciprocity. I think we could use law of reciprocity. Can we use law of reciprocity? Let's see the condition. Relatively prime. Okay, so you need to make sure relatively prime. I think relatively prime is very important here. Okay, because if not prime, if not relatively prime, that thing will automatically 0 already. Otherwise, use reciprocity. Okay, already reciprocity. Okay, so is there any way to see their relatively prime? Is here, this number here. So maybe let's write down the prime factorization. So 2 of 309, so 3 times 103. How about 103? Is it a prime? Looks very prime. Prime? Okay, you try and prove that it's prime. Is it prime? So I mean like square root 100, right? So 1 to 10, is it divisible? Divide by 100. Okay. 1, 2, definitely no 2 lah. 3, 3 no. 4, 4 no. 5, 5 no. 6, 6, 6, 6, 6 no. 7, she no. 8 is prime? Yeah. Yeah, it's prime. Okay. So this is the prime factorization. So you want to ask whether 3 can divide this whole thing or not, or 103 can divide it. Okay, so if 3 cannot divide this thing, right, 3 have to divide both, right? So 3 won't divide 7, first of all. No story already. 103. 103 cannot divide 143. Cannot divide 7. So they are relatively prime, so I think you should use quadratic reciprocity to reduce this technique. Is it easy to reduce? Is it easy to reduce? I think there's a reason why they write like this. There should be a reason why they write like this. Even if we use quadratic reciprocity, right, is it easy to reduce the big number here? What do you mean? Why? Why can modulo come? You mean modulo 309? Modulo what? Yeah, after we do quadratic reciprocity. So have you computed what are they mod for? Haven't? Okay. Either plus or minus the swap, right? Depend on what mod for, right? You said that this is easy to take mod. You found a way to see mod, maybe? You should, actually you should. Is it easy to take this mod 309? Any quick way to see? Any quick way to see? Or you really have to compute. Maybe you really have to compute. Like this, 343. So 343 maybe divide by 3, you get 34. Wow, so many 34 pops out. So this one will congruent to 34. Wow, 34 pops up again. Crazy number, huh? Can we reduce again? Is this right? So 34 square is what? What's 34 square? Easy to compute right here. Sorry, 2 what? One or one 5 6. So this one become 17. No? How about mod 309? What do you get? What's the remainder? I think if you take the negative version is smaller. 238. 238. 238. What is it? Is it 238? 229? You get 229. What's the other one? What do you get? 238 or 229? 229? 229? Okay. If it is 229, right? Can I suggest we get negative 80? Maybe it's easier to manipulate. Okay, let's get negative 80. Oh, still very big. Oh, is this question so crazy? So let's do like negative 80 times negative 80 squared. So meaning I reduce to 8 of them. Okay, I take square. Huh? What do you get? 6,400 mod 300. 220? What? You found easier way? Oh, right. Even smaller, huh? Use the phi, use the phi, use the phi, use the phi. Okay, wait. Let's split first. Okay. Maybe someone can go down this route. See what you get. Okay, let's do what you say. You know why I like to ask you? Because you've gone through these exercises, right? You actually have more experience than me. Yeah, because you play around with it more time than me. I'm just telling you like general knowledge. So because when you see these things, you will be more sensitive if you play a long time with it. So let's try what your friends say. I think I sort of get your idea. There's a reason they write in this way, you know. There must be a reason. So I think your friend found it. Okay. So have we decided what's quadratic residue we are using? +1 or -1 when we solve? What's the 309 mod 4? 1. Okay. Or as long as you got a 1 mod 4, you should be using the positive one, right? So don't care the other one already. Okay, good. So you say that we use the property of Jacobi, right? Yeah, so very important. Just now I just told you. So let's split it first. I think I see what you say. Okay. So you want to reduce mod 3, right? So in this case, it is a prime. So you will use the Euler. Oh, sorry. 103. You're gonna use Euler stuff? Okay. So how about you come here? You come here. You come here. You come. You don't need to tell me. You tell them. Yeah, tell them. You present. So nervous. Okay, so and maybe I write here. So 7102. 2. Eight, 3, 2, 6. Power to 51 plus 142 equals to 1 plus 142 or 3. Then it becomes 143 because model. Another one also can do like this. 42. 7, 102 plus 142, then it become very obvious because this is a prime because 102 is a prime with step 5 we can get 102 then plus 1 plus 142 then also get 143. And if we go back to here we can see very clear 143 divided 43 103. Then continue to use Jacobi to become very easy to see.
You can say like what here?
What theorem? Is it error theorem?
Oh yeah.
Error theorem. Why not you just continue here? You can just continue, right? What do you get? One. This one just go to 1. Since that's 2, right? 七杀11 21. Right, this is 2. This one is also 2, right? No, this one is 103. So this one is 40. Okay, so can you continue yourself? Is it okay? Yeah, you can continue yourself, right? So should be pretty straightforward. 40 over 103 is not prime. Please don't use quadratic reciprocity. You should split further first. Let's split to what? 2 to the 2 times 5. Okay. Maybe split one more, then I leave it for you to do. The 2 and then 5. No, 5. Actually 3, huh? You need 3 of them. Yeah. Right. But then 2 of them can be combined to 1, right? So you just left with these 3 terms you need to compute. Okay. I guess this one you have formula, this one you have formula, but this one you need to use quadratic reciprocity again. I think. Solve again. After quadratic reciprocity, you are left with 3 over 5, right? 3 over 5, I think we just computed, right? Just now. Did we met 3 over 5 just now? Yeah, we met 3 over 5 just now. So, yeah. Yeah, we met 3 over 5. Okay, good. Okay, I'll leave it for you to finish up. Okay, next one. Question 2. Let's finish question 2 and then we will break again. So question 2, continue fraction. Okay. Find the simple continued fraction expansion of x. You know what to do here? What's the algorithm? What's the algorithm? Alpha 0 is x, And then A0 is the floor of alpha 0. Okay. And then alpha 1 is what? 1 over alpha 0 minus x floor, which is A0. And then A1 take the floor again. Make sense? Okay, so maybe let me show you. 31 over 33. Okay, so first you take the floor. So the floor should be 1 plus what's the rest? So this one is let's write in the original form, I mean like original way of writing. So let me show you. So this is A0. And then what do you left with? 8 over 33. Then we can turn this around. Okay. And then what's the floor? The sky here. Huh? 5. 2, 2, 2. Yeah. Right. 2 plus 5. Okay. So I was trying to figure out where's your alpha 1. So alpha 1 is alpha 1 is this guy. This guy is your alpha. So your alpha 1 is alpha 0 minus A0, which is 1 over which is 1 over A. Your alpha 1 is the bottom guy. This is your alpha 1. Make sense? Does it make sense? I am trying to show you like the original way of doing continuous fraction and the formula. Okay, where this alpha 0 A1 allocate inside this combination. So then this is alpha 1. Then the 2 here is your A1. Okay, the number 2 here is your A1. Okay, then you continue. Make sense? Okay. All right. So you can see that this alpha I, right, skip the step here. Let's skip the step. The step. So straight away jump to the step. Then find the floor and then come to 1 over that thing. Okay. Really, we are skipping this step here. Wait, this one. Okay. Okay. And then find the all the convergence of the continuous fraction. All the convergence. Is it possible to find all the convergence? What do you think? Is it possible? Before finding it, is it possible to find all of them for this case? What do you expect here? This is a rational number. What do we say about rational number? This has a finite. Is it called finite? Finite continuous fraction, right? Yeah, so meaning it stops somewhere. Okay, so you can find all of them. Or sometimes if it is periodic, you also can find all of them. If it's not periodic, it's very hard to find all of them. We need to calculate it for the mean. Okay, you know, still remember what is convergence? The C0, C1, C2, so truncated. Okay. And then find the simple continuous fraction should be similar, right? This one. But then I think there's a technique I want you to remember for this kind of question, right? You could squeeze, for example, you could squeeze 13 in between two perfect square first. Okay, so first perfect square is 9, second one is 16, so that you can really squeeze this number in between two integer that differ by 1, 3 and 4, so that you can find that the floor of square root 13 is 3. Okay, so it's important that this upper bound is +1. Okay, otherwise we don't know the lower bound is really 3 or not, the greatest lower. And then how about C? What do you do here? You what's the technique you should see here? Use the S technique, right? You replace the repeated pattern with the original S. So the first two you should ignore first because this is not repeating. So you just solve for the repeating pattern first, and then you plug this X into this original thing here. Does it make sense? Okay, so what I meant here is you have to solve X equals to 1 semicolon 1 2 first, and then you plug this back to this like that. This is your Y. You need to complete this Y. Okay, so two parts you need to do. Using the convergence of the simple continuous fraction exponential of pi. Okay, this one I give you in the class of, so you have this convergence. Determine the best rational approximation to pi whose denominator does not exist by 50,000. Okay, so what do you think about this? This is one of the abstract things we talk about convergence, right? Okay, so you need to use the theorem. I don't think this will come out in exam, but I will confirm with you. This is just about your assignment. Okay, so did you remember the sum property on convergence? So, is this enough? No, you want rational approximation. Okay, let's see. Rational approximation. Rational approximation. Is this enough? Rational approximation. Rational approximation. Let's see. Using the formula determine the best rational to pi does not exist. Best one. Do we have a better does not exist? Does not exist. Okay, what do you think? If you use convergent, you need to find the best rational to find. Wow, seems like a bit long work. Okay, so first of all, you have the convergence from here. Okay, first of all. Hopefully this is long enough for you to compute. There are like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm not sure if 50,000 is where, but hopefully this is enough. Is this enough? 50,000. Should be enough. You see from this example, 1, 2, 3, 4, 5 already almost 50,000 already. I think you just need to go to 6 and 7 already go very big already. So first five or 6 is already reaching what you want. Okay, so no need. So you just need up to 1, 2, 3, 4, 6. Maybe around here is enough to check. Okay. Hey, hello. Okay. So if you look at this question, this example here, is that using some probability we see that this is the best estimate with denominator less than or equal to 1, 1, 2. Okay, because for the next one is already 1, 1, 3. So the best rational approximation with denominator less than or equal to 1, 1, 2 is this one. Okay, but we care about 50,000, right? Okay. So I guess we need to make sure that the next one is already exit 50,000. If the next one exits 50,000, that means the fifth one is the one that is closest. That means you still need to check one more actually. Is it that crazy at this question? Let's check the answer. Let's check the answer. Let's check the answer, see our idea correct or not. Wow, seriously, they compute until A6 or it's crazy. They really compute until A6. You see? Because F5 is not enough, because F5 not exit 50,000 yet. Okay. So it turns out that A6 is good. So the fifth one is the best rational. What's this? Happy New Year. Chinese New Year. Happy Chinese New Year. Okay. Yeah. What happened? Firecracker. I think it's firecracker. Someone come because you know the A4 parking they block it. So it seems like someone is coming. A4 parking car park. Lower ground. Yeah, I don't know what event. Okay. Everyone okay with this? Is it okay with this? Okay, so you found the largest denominator that's less than 50,000. Okay. Turns out it's A5 because if you compute A6, it's already exit 50,000. This one, the denominator is Q. Okay. Never think about the if this crazy. Okay. Yeah. Any questions so far? Should we take a break? Or you want to continue? And then we can finish earlier. What do you think? Huh? Just finish this and then we finish earlier? Huh? Okay. Okay, can. Okay. So let's go on. Pythagorean theorem. Hey, where's my assignment? Okay, here. Next. A primitive Pythagorean theorem is a triple. Okay, this one we introduced yesterday. Okay. List all the primitive Pythagorean triples we see less than or equal to 60. Give your answer without repetition and justify completeness. Okay, this one we did yesterday, right? We did it for 25, right? 25. Okay, now they do it for 60. Okay, just see what they did. I think it's very similar. But justify the completeness. Okay, see how they justify. All right. So, well, they use this two number here, right? M and N to control this three number here, like what we discussed yesterday. Basically, see. Mm. Okay. Let's see again. Okay, so they use this lower bound of n, okay, lower bound of n to check what? To check the possibilities of m you can get. Okay, so it turns out that you can reduce the possibility of m up to 7. Then you just need to check up to 7. Is everyone okay with this bound here? Okay. With this bound here. It's just saying that this solution for n Could be 1, could be 2, could be 3, could be 4, could be 5, could be 6, but we put the lowest one first to figure out what's the possibility of the others one. And so in this sense here, we just need to check up to 7. So if you check up to 7, there are these solutions. If they take the multiples, these are not all of them, right? Because we can take multiples, right? Oh, okay, because, okay. In this case here, we just care about primitive Pythagorean triples. We just care about primitive ones. So meaning what? Their GCD is equals to 1. Okay, their GCD is equals to 1. So when you check these pairs, right, that you need to make sure their GCD is equals to 1. So since there's no repetition occurs, these are the primitive triples. And then it is complete, okay, because we have exhausted all admissible Mn with n less than good. Yesterday, the one we don't care about primitive, right? We just care about Pythagorean triples. If you care about just Pythagorean triples, you need to consider all the multiple as well. Is it clear? Yeah. Because why is it enough to just consider the primitive one and then all the multiples? Because if you are one of the Pythagorean triple, if the GCD is not D, you can always reduce to the primitive one. So that's why it's enough to just consider the primitive one and the multiples one. They will consist all of them. Otherwise, you can just divide by GCD or divide by D by C, and then you can get back to the primitive one. But in this case, you just care about primitive. So no need to care about multiple. The question just asks about primitive. Okay. Next, determine all primitive Pythagorean triples satisfying C equals to B plus 1. Justify that your solution are primitive and no other solutions. Okay, so what's the idea of this one? Okay. Well, I think this one is kind of straightforward. Let's see. So, well, to satisfy Pythagorean triples, right, you need a squared plus b squared equals to c squared. But this question says that this c is special. This c have to come from b plus 1. Okay. So then, let me straight away solve this. I think we could straight away solve this, right? Let's play around with this. So b squared plus b plus 1. So I can remove b squared from both sides. Then this is equivalent to solving a squared equals to b plus I. Easy to solve it this way. So what do you mean? Oh, to be, thank you. To be. Determine all. Can you get all from here? Okay, one way I can think about this solution, right, is using this. So there is some intersection between the function of x squared and 2b plus 1. I mean like 2. So this is x squared, the other one is 2x plus 1. Should I use this way to solve it? I think let me think. This is what I wanted to do. Let me think. Yeah. You mean use the one that we had just now? Substitute? You mean use this? You mean use this one? Use this formula? You're saying this? Is this? Easy to see answer? You think so? We could try also. A equals to m squared plus m squared b equals to 2m and c equals to okay. Oh, this one is minus. Okay. You see, you mean we need to plug it in? Okay, so you say that this one plus this one equals to 2mn plus 1. There's something we could do here, right? I'm very tempted to factorize them actually. So if I factorize them, I get minus n. Cannot. Huh? So it's positive. Wait. So from where?
Because
Mm.
not where did they
Mm.
and
Mm. This one is positive. Sorry. Wait. Okay, wait. So I'm just now I was checking my factorization correct for this one. And then you say that m have to be greater than n. And then what's the one? Okay, I get what you mean. Okay, but because this implies that m minus n is plus minus 1, right? But then m greater than n implies that m minus n should be. So this implies that m have to be equals to n. M equal to n? Oh, sorry, 1 plus n. Sorry. M have to be equals to 1 plus n. Coming order. I think we're not done yet, right? Substitute back. If I substitute back, what do I get? Substitute back. Then a is n squared plus n 1 plus n squared. A is 2 n. So this one is n squared. And this one is 1 plus 2n plus 2n squared. 2n squared like that. Then how to make sure this GCD is one? 哪一个 B？ 喂，什么 B 是什么 ？B 和哦，OK，good，啊，什么出来？啊，对，啊，OK，make sense，啊，make sense，yeah，OK。So how do you make sure that GCD is one? So this one is an odd number. This one is always even. Even odd doesn't matter. Mm-hmm. Huh? C must be odd. Yeah, C is odd. Yeah, C is odd. Yeah. Uh-huh. Sure. And then, but then we need primitive. How this condition comes in? All the primitive. How the primitive things come in. Any idea? Normally, if I don't have idea, I go solve easier one first. And then I come back. Yeah, this is the thing you have to do. You cannot stuck there forever. Okay, we can solve. I think I can solve 4 first. Okay, I can come back soon. Okay, I think 4 is pretty soon, pretty fast. Okay, 7, 8, 9 cannot be written as a sum of 2 square. I think we have a property here, right? What's the property that say we cannot write as sum of 2 square? Is it in a certain form? Sum of 2 square. What's the form that you need? Sum of 2 square from yesterday. The positive end if each prime factor occurs to an even power. Okay, so meaning, can we split this up into prime first? 7, 8, 9. Okay, 3 times 200. Huh? 6, 3, 6, 3. Okay, can we split 2, 6, 3 again? And the nearest perfect square is 16 square. 16 square. About there, about there. So you need to try about until 16. Looks very prime, this guy. Is it prime? Yes? Okay. Pretend it's a prime first. If it's a prime, but you need to check, see if this is a prime. Okay. If this is a prime, 4 to the 4k plus 3 occur to an even power. So you can see that this is 4k plus 3, right? But there's only one of them. It's an odd power. Okay. So if you want to write it as a sum of 2 square, any 4k plus 3 integer factor must occur to the prime odd even power. But here only odd. Okay. So it's not. Is it okay? So try check. Okay. I think no need to check lah. If 3 is not dividing 263, then you cannot get another 3 already. Yeah, then you can basically call again over. Okay, because 3 is not coming out. 3 is not even power. Because it's not divisible by 3. Okay, prime doesn't matter anymore. Okay, next, sum of 2 squared. 97. I think it's a prime in this guy. You cannot split out. It's a prime, right? I think you just try an error like this one. Yeah. 999 is a sum of 4 squared. Well, this one you could try 9 times 11. Sorry, 111. 111 is a prime or not? I think it's not prime. Oh, okay, good. So 9 times 3 times 37. 4, yeah. So then you can do for each of them and then you combine them using the formula. Can or not? Can 999 written as a sum of 3 squared? This one we just see right just now. So this is like 3 to the cube times 3 to the times 37. This is far from the 4k, 4 to the k times something 7 mod 8, right? Yeah, it's far from this form. Okay, so cannot. We're very far from this form here. Okay, so cannot. Okay, we solve everyone except this one. GCD, yeah, how GCD comes in here? When not working. Determine all primitive. GCD. Okay, C equals to B plus 1 means what? It just means that this one already care about the parity, right? If A even B odd, then. But how they care about divisor, right? I think this really needs to take the whole thing here to see. I see the whole thing here. I need to make sure their GCD is 1. Any idea how this GCD condition comes in? Any information we missing? Primitive. Let's read the question. Determine all primitive. Satisfy this. I think yes. I think this one is this more useful or not? Because previously when we solve for primitive parameters triples, right, we try to restrict our A and B. A and B that we can control here. A square. This is A square. This is not 2D, or this is like think about it as 3D. Because because any idea? Right now. Yeah.
这个不是这样，这里是讲这个公式就是我分每天。
Oh, okay, okay. But then we need to find. Okay, okay, good. There's some more condition coming in here. Yeah, that's why I say we are missing something. So this statement says what? So whenever you start, try and read back your notes because something is missing. So if you want to make sure x, y, z is primitive, just make sure the m and n is primitive. Oh no, yeah, relatively prime. Okay. Okay. It's better. Does it help? Relatively prime, and then satisfy this. So we have two conditions here. So GCD of Mn to be 1, then M is n plus 1. So meaning you need to find and let me write here to find C. So to find A, B, C primitive with C equal to B plus 1, it is equivalent to find from this derivation that M N GCD, so to find M, okay, to find M N with M equals to 1 plus N, it's very similar. And yeah, GCD is 1. Is it possible to do this? Does this always hold? This one agree so far? Is it okay? Does this always hold? Like 3, 4 also work, right? 5, 6 work or not? 6 also work, right? But 5, 6 will give us inverse triple. Seems like any number will work. 6, 7 over there. 7, 8, 8, 9, 9, 10, 10, 11. Everyone works on. Isn't it? Can we prove that the GCD is always 1? No. No, wait. It's on. Yes, right. Okay, so seems like all. Okay, so I feel like proving this proof. So m plus 1 and n, the GCD is always 1.
To prove this, use Euclidean algorithm.
The GCD. Otherwise, I have no control. What's Euclidean algorithm?
Yeah, why sound stupid?
Yeah, let me think. Maybe it's a very easy fact. How to prove this? GCD tokens 1. I don't know what is n now at the moment, but then
How do we prove something? How do we find GCD again? Euclidean algorithm. Is it? May think. Yellow Euclidean algorithm. Other than that,
what does Euclidean algorithm do again?
how do you find? So you take the remainder and then you divide again. You get the remainder and then divide again. Right?
So
Equal to 1 and then your GCD is 1, right?
so can I say like by Euclidean algorithm? Okay, so by Euclidean algorithm, n plus 1 is equals to n plus 1. Like that. And then if you really like, then n equals to 1 times n, right? Plus 0. Then your algorithm stop. Uh, uh, so this is your common device, greatest common device. Some of it should be. Is there any direct way to see it? Huh? What? What is always good, yeah? Huh?
But odd and even could have no man. Got that. No man. No. Got that. Like 6 and 9. The problem here is plus 1. Is the next one. Next one more restrictive. If you just randomly pick even and odd, the GCD could be greater than. The problem here is the plus 1. But from Euclidean algorithm, you can see that. Yeah. I was like thinking is there a more direct way to see. It should be there. In that case, there's a lot of MN. Every MN will work. Let's see the answer. Ding, 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 ding. Okay. Let's see. See the same thing. Get the same thing. Then up to this stage, we are the same. You see?
this stage we are the same. M equals to M plus 1. Conversely, okay, it says that if you have N, they also reach this, you see, BCD. Okay. And yeah, so it's really for any positive integer. Yeah, anything will work. Why is it anything will work? Because you have to prove this actually. This answer didn't prove to you. But then we prove it, right? We use Euclidean algorithm. Yeah. Yeah. Actually, any n will work. And then m is just 1 plus n. Okay. Yeah, we almost hit every point here already. Actually. You know, this conversely means what? It just says that if you want to solve it, your solution have to look like this. If your solution look like this, you can solve it. That's it. So these are all the solutions. Yeah, so there's really no condition of n. N will determine your n. Because this thing is always true, so this condition doesn't have much thing to do with your solution. Because n plus 1 and n, the GCD always 1. Or you can use Euclidean algorithm. I'm pretty sure there's a faster way, I guess. I mean, not faster way, but definition. Let me think about it. I can get it. Why they did this n not congruent anymore? Only this point. So the resulting triple is primitive. Resulting triple is primitive as long as this one is congruent to 1, right? I mean GCD of the mix 1, right? There's no other condition, right? Oh, okay. So their parity, okay. So it's talking about their parity. 1 even, 1 odd. But then we know that if it's plus 1, then 1 must be 1 if 1 even, then 1. And so that's that point of m not congruent to n mod 2. Do you understand? Because if they are congruent, the same mod 2 meaning what? Both of them have to be odd or both of them have to be even. And so this is the other way to say this. Okay, 1 even, 1 odd. So they are congruent to 1 odd. Okay. Yeah, this theorem is important for this assignment. Okay, here's a special okay. Okay, any questions so far? Any question? Any question? No? Yeah, we almost hit all the points, just that we need to put things together. Okay, and then just now we explained this step in. Okay, why is it what? We use Euclidean algorithm. Okay, we solve it in like an hour. No wonder my student do my assignment in 1 hour.
1 hour.
No, they left it to the last day to do, you know. Then they complain to me, oh, your assignment is very hard. Eh? Why you left until last day to do? Yeah, so please don't leave your homework until last day. Okay, do it every day, every time a bit. And usually assignment is very hard. Harder than people, harder than test, harder than your exam. Okay, so you need to digest the question. Okay. If no problem, then we dismiss. I'll see you on tomorrow, then we'll do revision. Without question.
Hello，被 professor。
明天再改不行。